Major funding for this program is provided by State Farm Companies Foundation. Additional funding is provided by Caterpillar, the Gordon and Betty Moore Foundation, the Intel Foundation, the Motorola Foundation, and the Society of Manufacturing Engineers Education Foundation. Outreach funding is provided by National Instruments, Rockwell Automation, Rockwell Collins, and Xerox.
It is exciting to be on the cutting edge.
Advancement of this kind of technology requires a lot of perseverance.
Anything can go wrong at any time. You have to be on your toes.
It's like a puzzle or a treasure hunt.
With failures comes success, and that's the way we advance the technology.
To be part of a pioneering effort that will generate change is the experience of a lifetime.
Who are the innovators? Men and women around the world who are improving our lives, finding new technologies to help us communicate better, travel efficiently, and live longer. In order to solve today's energy crisis, innovation is critical, and there's no single answer. Lots of teams are looking for creative solutions. You're about to meet one of them, people who think a lot about what happens above the water and below it.
We've been working towards this moment for a very long time, so there's a lot of nerves.
The ultimate goal of the East River project is to be able to produce energy from the water. If the project succeeds, it means we would have an amazingly green source of energy.
We have a small company, and we're bit off a lot. We're putting a new generation of turbines in the East River in New York City to generate power. They are designed to provide power for the supermarket and a large parking garage on Roosevelt Island. The original turbines were mounted on the bottom of the East River in 2006 and 2007. They are 5 meters in diameter, which is 16.4 feet. They handle a lot of force from the flowing water.
I'm nervous and I'm excited at the same time.
Over the course of the project, we've had a number of different failures, most of them centered on the blades. And it led to blades physically breaking in half. The current in the East River has turned out to be faster than what we originally expected. And so the point of this installation is to test the new blade design.
The mood is anxious right now. There are a lot of stresses. Coordinating dive work, boats, equipment, all of these things have to come together. And it's a challenge.
Our company comes from all over the place.
It's a virtual company. We do most of our business via email and phones.
I saw you. It's great work. A whole team of people has come together to build these things and do all the millions of things that have to happen for it to work. And that team is just amazing, absolutely amazing.
I'm an engineer and a designer. I mainly design and work on any piece of the turbine that's underwater. I was very involved in the redesign of the blades.
It was kind of one of the first designs I've ever had that was manufactured and then put into actual work in the field.
I'm from Atlanta, Georgia. In high school, my soccer coach was also my trig teacher and a physics teacher as well. And
he really went out of his way to encourage me both in his class and on the soccer field to take my love and aptitude for math and science and run with it.
This is good. We got to figure out how to use that velocity data.
I love problem solving. It's like a puzzle or a treasure hunt. It's really exciting to solve those problems and then see the final answer.
This is a good story. Did we hear about it?
That is absolutely amazing.
When we're thinking about going into a specific location anywhere around the world, they'll come to me and ask me to study the conditions of that location and determine what sort of energy we'd be able to produce. So I use water velocity modeling and energy modeling to determine those answers. How we're getting energy from our turbines is very simple. The movement of the water will rotate the blades on the turbines themselves. This rotation actually turns an induction generator and they produce an electric current. This current then gets sent through a cable along the bottom of the river into our control room. I have a bachelor's in physics and a master's in geophysics. My job is never the same. There will be moments when I'm working very intensely on programming and I'm analyzing data. Then there's another week where we're building turbines and we're painting turbines.
And you have to be able to be flexible, and I love that kind of environment.
When I was really young, all of the boys around you are convinced that you can't do math. And so my goal was to do math. And then as I became much more independent and much more ambitious, I realized, even if you don't see that many women who are physicists, I can be one anyway.
Verdun. I'm not an engineer by any means, but I'm kind of a handy guy, jack of all trades. The nutshell of me, born to a Scottish mother in England, Pakistani father, was adopted at the age of 2, lived in England until I was 13. Moved to the United States in 1987. I was in the Army 4 years as an officer, then became a stockbroker. I was in the World Trade Center and luckily enough survived it on 9/11. I remember looking up into the sky, and all we could see was kind of a black soot. I was walking away from the World Trade and looked back, and the building came down. What goes through your mind when you see something like that is all of those people dying, and how helpless you felt. I really feel very fortunate to have the life that I do. I don't ever take it for granted. I think I changed. I think my values had changed, how I envisioned my life. I wanted to feel like I was making a difference. I really think that this is where I need to be. I think I'm in my groove.
If we can prove this technology today, which I'm hoping we can, it means the future of our company and the future of this technology.
Because this is when investors come, this is when the media comes, this is when politicians come, this is when anybody who has an interest or a stake comes.
I think that's the part where it gets scary. You start thinking about what can go wrong, will go wrong, and will it go wrong with all the press around? The only hope is to keep your fingers crossed.
There are a lot of details that have to be looked at. When you're putting things in a body of water where it's hard to get at them, it's sort of like sending a satellite into outer space. And there are a lot of steps that have to take place in sequence to make the installation of the turbine successful. It's really choreography.
Boat coordination, dive coordination, everything has to be ready to go.
You have a very, very short window of opportunity to install the turbine. It's not safe to have divers in the water during peak currents.
There is about 45 minutes to an hour during every change of the tide direction when the water is slow enough for it to be safe for a diver to be in the water before their lives are in jeopardy.
13:15, they're going down to complete the installation.
The divers have to enter the water with their tools, get to where they're going, where the turbine is. Just getting out there is a stressful occurrence. And then the divers have to attach the turbine to a metal clamp, which we call a pile adapter, and that secures the turbine to the river bottom. Once the turbine's bolted to the bottom of the river, a smaller boat that we call a Johnny boat has a couple of people on it. They take the cable that is attached to the turbine and bring it to shore. So that we can then route the cable finally into the control room and actually hook it up to the grid.
So you move very quickly.
The diver's final task is to remove the blade sling from the turbine itself. The blade sling is a nylon strap that restricts the turbine from rotating. Once you remove it, it actually allows the turbine to rotate freely and then to produce power.
Final thing ought to be to pull off the sling. There's the blade sling. The current should be just about ready to switch, which means in the next 30 to 45 minutes, we should see electricity being generated.
The media is there, everybody is watching. It's a tense period, but also a very exciting period.
All the engineering and all the logistics and all the operations and all the money and all the effort and all the sweat, it's all on the line.
We're looking for a green light to come on and let us know everything's okay.
Uh-oh. Okay, no.
As soon as you see that green light goes on, that means power is being generated into the grid.
We're getting very close. It's going to happen any moment now.
And it's, you know, a little bit like mission control. We're all staring, you know, tension's high.
Everybody is watching and waiting for just the right moment when it'll turn on.
There we go. That's it.
There it is. Hot dog.
It was like, oh, we saw the light, we're powering, everybody can go home. And then it was like, oh. The light went out.
I think everybody wanted to cry. Pretty much, I wanted to cry. I think people probably wanted to kick things.
It was pretty nerve-wracking, and we basically had to start troubleshooting immediately.
The engineering team just basically jumps on this thing like a grenade. Hannah's running manipulations on the computer, try and glean as much information to find out what happened, why did it happen, and what caused it.
Jonathan was looking at the power signal to see when exactly the power stopped being produced. Dean Corn was thinking about everything.
You get the short trace. It is?
It's probably a triggering thing. When things go wrong, you want to get input from different people who may have different ideas, and nobody has a monopoly on the good ideas.
Can we just print each figure and bring it down there or something?
Great. Okay.
We all stayed there till 11 p.m. that night, trying to figure out what was wrong.
Look at the power.
Yeah, I'll get to the DAX.
Once Turbine 3 had its failure, we realized that we had to remove it from the water.
We had come to a really strong conclusion that there was a leak inside of the turbine and that water had gotten in. The blades were still good, but the generator was bad. But we had another turbine with a good generator and no blades.
Since the turbines are modular and you can take parts off one and put them on the other,
we basically pulled out another turbine and swapped parts.
we took the two turbines across the river to our work site to clean them up and switch out the blades.
The engineer's job is not only to find and solve the problem, but to actually make it work.
You're actually pushing the boundaries of what you're able to do when nature basically tells you no.
Today we're putting the turbine that we fixed back in the water. It's a big, downer. When you expect things to work, you anticipate they will work, and then something out of the blue just, stops it, because then you've got to figure out what it is.
But it's a real-life scenario, and things like these happen. You don't get from A to B without some trials and testing and redesigns along the way.
It's very hard to have the world witness your own best guesses a lot of the time, and that's really what we're doing right now. We're all trying to figure out how this technology works and how it can be improved upon.
We have a long ways to go. We have a lot of problems to overcome in terms of technology and economics and the current market. But it felt great knowing that we'd pulled together as a team.
Everything's good to go?
3-minute mark. We got power!
I'm going home. Bye. We finally got the word that everything was working, and just basically did this. I wouldn't say it was a big hearty Bronx cheer or anything, but we were definitely relieved.
Okay.
Oh.
Yeah.